Hello, everyone. We are Footsies, and we created a electromechanical medical shoe. We are an interdisciplinary team of 2 mechanical engineers and 2 electrical engineers. I'm Cody. This is Kelly, Julia, and Eshe. I'd also like to introduce you to our very handsome marathon runner, Bob. He has just completed his 50th marathon. Congratulations. However, 2 weeks after the marathon, he injured his right knee. Very common with someone who runs that much. So he needed knee replacement surgery. Unfortunately, something happened during the knee surgery. It's very common among medical professionals. It's known as nicking the nerve. Nicking the nerve involves severing a nerve, which prevents you from then lifting your foot up and down. This is actually something very common among a lot of people, and it's called drop foot or foot drop. Drop foot results in a patient unable to lift their foot, and it causes a lot of issues while walking. The patient ends up slapping their foot against the ground, tripping, dragging their foot, a lot of issues, and it's caused by a variety of different things, including the knee replacement surgery, MS, diabetes, stroke. So there's a large opportunity for people to, there's a large number of people affected by it, and there's a large opportunity for something to correct this. And that's where we come in. We created a medical shoe that lifts, clearing the ground while walking to help people with drop foot. And that's why we don't lift spirits, we lift souls.
No sound. Cool. Imagine.
So to talk a bit more about our product, we're first going to talk about gait cycles. If you're unfamiliar with what a gait cycle is, it's the process of how you take a step. If you look at the animation above, you can see that your heel striking the ground is the first part of that. Then the rest of your foot hits the ground, your other foot lifts, and your toe leaving is the last portion of that step. So like I just said, for a typical foot step, your foot should be raised as your heel is approaching the ground. With foot drop, however, your foot isn't able to lift, so it drags along the ground like you can see in the picture next to it, which can lead to a lot of issues. With footsies, however, we're really trying to get back to that original footstep. Again, with a more expanded gait cycle, you can see with foot drop, you can have foot crash, tripping, falling, and a lot of serious injuries with that, which is really something we're trying to avoid here. But to step you through in a bit more detail, this is our gait cycle with using footsies. So during the heel strike stage, we're using distance sensors and accelerometers to sense as you're approaching the ground, to know during the foot flat stage to lower the foot to the ground. During the mid-stance stage, your foot is stationary as your other foot is lifted. And then during the toe-off stage, again, the distance sensors and accelerometer help you know as you're leaving the ground in order to raise your foot for the mid-swing stage. To help translate the gait cycle into something that we could actually use, we did a number of analyses. The first of which was our static analysis, focusing on the pressure along the gait cycle. With this, we saw that the max pressure was during the toe-off stage. And we had all of our electronics in our PCB there, so we really wanted to make sure that this was well protected. So we performed a finite element analysis simulation with a 2.5 safety factor to make sure that all of these were protected. We then moved along to our dynamic analysis. As you can see, we have a free body diagram with a 1 degree of freedom system. This was just to see how our lifting mechanism worked. And with that, we had our motor selection of balancing torque to make sure that we had enough torque to lift the weight of the foot and the shoe, but also balancing that with the walking speed. Now, Julia's going to step you through a bit more of our product development.
Thanks, Kelly. After talking to over 20 clinicians, gait researchers, and our medical advisor, we grounded our medical need with the needs of the user. Then we did an engineering analysis based off these biomechanical considerations that Kelly just walked through, and we made sure that we considered some recent technological advancements in the development of our shoe. This allowed us to create a medical device that was unlike the traditional orthosis. For example, the Internet of Medical Things. With our Wi-Fi enabled chip, we can send gait data from our shoe in real-time environments into the cloud and have analysis of that data later. In addition, Adidas has started 3D printing their shoe soles and mass manufacturing it in that way. And this has allowed us to design a shoe for 3D printing. We took a very iterative approach to our product development. As you can see here, we started with proof of concept of the lift mechanism, continued through electrical mechanical integration, and then fitted into the form factor that we wanted. This allowed us to stay on the same page between our electrical and mechanical sub-teams, as well as check in with our advisors and clinicians and made sure we were talking about the same thing. Our final deliverable is a 3D parametric CAD model that allows us to fit this into standard US shoe sizes. Throughout this development process, we made sure to consider all of the regulatory standards involved, especially, as Kelly mentioned, protection of our electronics. So the lithium-ion battery is protected very well from the patient's weight and the environment. Footsies is an integrated smart shoe and paired activity tracker that improves the daily mobility for foot drop patients. What that means here is that it's a 3-step process of 2 distance sensors on the bottom of the sole, checking how far away from the ground the shoe is, the custom PCB telling the motor when to lift and clear the shoe during the mid-swing step of the gait cycle. All of the electronics are fit into the midsole layer, which is below the foot and above the sole, which includes our battery, distance sensors, motor, and custom PCB. The PCB was designed to fit within that tiny enclosure in the toe to fit our shoe design. Yeah. In addition, we've been developing a paired activity tracker that allows data visualization of the accelerometer and step data of the patient. And this provides benefits for all the stakeholders. The users just get that daily step count that shows how they've been improving over time. The family can see whether their loved one has fallen, and after a predetermined amount of time, send them a trip alert. And the clinicians can see very quantitatively how the patient is recovering over time. Overall, that allows us to quantitatively assess foot drop patients in a way that other devices cannot. And now that I've talked through the development of the Footsies product, Etche will tell you how that fits into the current market.
Thank you, Julia. So we looked at some market data to understand the opportunities that are available, and it is expected to see that the global skeletal support systems and orthopedic devices systems are expected to reach to $5.8 billion by 2025, which is a very promising number for us to enter. And we also looked at some of the big competitors in the market, such as Medtronic, Abbott, General Electric, and Johnson & Johnson. And we also identified certain products that are most commonly used. And the most commonly used one is actually the functional electrical stimulator that is not really providing any mobility to the patients, but providing an electrical sense that is forcing them to move their feet, which is not really comfortable to use in everyday life. And the second one is ankle foot orthosis device, which is basically a passive brace that is not really providing, again, any mobility. And the third one is exoskeleton that is not really available in real-time environments, but only at lab settings, even though it provides mobility. And Footsies is the integrated smart shoe that is providing mobility at the real-time environments. And as you can see, we created a competitive analysis of the overall market, which aligns the mobility versus low-cost versus high-cost accesses. And we're standing at a very nice point where we're providing mobility at low cost for our patients. With that, we're aiming to help people like Bob that are having problems due to drop foot, or as also known as foot drop problems, to help them live their lives in the best way possible. So we don't lift spirits, we lift souls.
Every time.
Thank you. Yes.
How thick are your soles? Because one of the problems with foot drop patients is that they're constantly dragging their feet and their toes. So how thick is this sole?
So right now you can see that's with a deconstruction of a current available shoe. We think an integrated design where the full shoe is developed for this would be much thinner. And with more advanced manufacturing, we could reduce the current thing you see by 30 to 40%. So I don't know, like yay high. Yeah, I wish we had a size reference. Do you want to go back? Yeah. So if you, I don't know which one of these is a reference, but that's a size 10 male shoe. But we could see that getting much thinner once we have integrated design. Yeah.
Yes.
If you consider, instead of a motor, something elastic, that way it's constantly pulling upwards, so it's not only when they're walking, or is that something?
So that's similar to what's already on the market, something that is constantly lifting it up. And we liked the option of having your foot move more naturally as your foot does normally. You can have it up, you can have it down, and like you have those options. So.
Yeah, we think that'd be a really cool future step for once we have all of this data, we can see how that goes back into the customizing the product for each user. So you could see like, oh, they're walking fast, maybe they need a faster motor or something like that, and having that data learned per patient.
Yeah, at the moment, though, that is why we're using the distance sensors and accelerometer, so that in real time, if you're walking slowly, if you're walking quickly, it's moving with you. It's not predetermining your gait.
Yes.
Since you're adding to the bottom of, in the midsole of that shoe, wouldn't that foot be more elevated than the other ones or be unbalanced when you're walking?
That's a great question. As we're giving these to patients, we would build 2 shoes for them and weight them proportionately so that they wouldn't be uncomfortable while walking.
Yes.
My concern is motor response time. If you have a motor that would be fast enough to deal with this, especially for someone that may want to run.
So currently, it's not developed for someone to run at. We based our current motor specifications on walking speed of the average person and took in an extra factor for someone who could walk a little bit faster than that. There are a lot of specifications that we went through with a lot of different research papers for as far as like torque for the motor and what specifications you need for that. And here you can see how the gait's divided, and at an average walking pace of 3 miles per hour, we have a certain amount of time in that to lift the foot, and that's what we based our speed on for the motor. And here's different torques and lifting forces of people in dorsiflexion from ages 5 to 80 that we based off the requirement for the motor.
Yeah, so actually part of that iterative product development process was that we were making sure we got the motor right because of the main components of being able to lift the full weight of the shoe as well as being fast enough. And so we chose a motor that had a couple different variations. So that's a $15 motor off Amazon. We could definitely get more power at a higher cost and a smaller profile.
Did you research using something like a piezoelectric effect or something that makes your keep the battery charged? Yep.
We looked into it. It's currently not the most efficient technology there is right now. The battery, the testing that we were able to do with the battery, it easily lasted the 8 hours of a normal day. There's really not a lot of current being drawn on the, through the motor, so there's not a lot of power needed. And our goal was to make it last 8 hours because that's roughly how much time someone's going to spend out throughout the day. One of our later goals was to create use induction charging so that someone could take off their shoes, put them on a mat when they get home, and then the next day they're charged and ready to go. And that's what we'd kind of like to aim for.
Do you see a day when Bob could run again?
Sorry, what was that?
Well, do you see a day when Bob could run again?
That's the hope. That is the hope. We
Pen relays next year.
With foot drop, it's usually, in most cases, it's not a permanent thing. It's something you're living with for a period of time. So Bob will be running marathons soon.
Is there any concern that you might also miss carrots and thus render your slogan?
We've made several jokes about that.
Grammar. That's
Good constructive feedback. I like this.
Thank you very much.
Thank you.
Thank you.